In the third mini lecture of aircraft response, we will discuss the aircraft response to the control movement. Remember in lecture 1 and 2, we only discussed the aircraft response to the gas which is stick fixed. Now let's see what happened to the stick free movement control. Okay, so now let's first introduce the aircraft input and output relations, a bit concept. So consider the relation is combined like this, and in the center is a mathematical model of aircraft dynamics. And so we can treat that as a black box. And on the left-hand side is input parameter, and on the right-hand side is the output parameter. So let's see. And since we are talking about the aircraft response to control movement, so the input can be what? Give you 1 second to think about it. Good. And so the input side we can consider as like the aileron deflection, elevator deflection, and rotor deflection, something like those. And also, since it's an aircraft, also there's throttle, and we also need to take that into consideration. On the right-hand side, it's just the parameters we're interested in, like the vertical speed, longitudinal speed, and some like the angular rate, right? And as usual, we want to consider the longitudinal dynamics and lateral directional dynamics separately, so we still can consider that way. Okay, so we can divide that by that model by the dashed line on above is the longitudinal dynamics, and below is the lateral dynamics. And for the longitudinal dynamics, we can consider delta E, that's the elevator deflection, and epsilon is the throttle angle. And then the output we are looking at is UW. U is longitudinal speed, W is vertical speed, Q and theta. Q is the let me see, PQ is a pitching rate, theta is a pitching angle. And for lateral dynamics, we need to consider the input, delta A, delta R, that's the aileron deflection and the rotor deflection. On the right-hand side, we have quite a few parameters. I'm not reading them. Okay, so now let's talk about the longitudinal response first. And first of all, let's use the elevator input as example, which means we have elevator and deflection, elevator movement. Okay, so let's see what kind of scenario it is. If the elevator is displaced by a given angle delta E, the right-hand side of the longitudinal equations should be an elevator turn. And why? Because in the stick fixed control we talked about in the earlier chapters, and the right-hand side, the elevator turn is usually set to be 0. But here, instead of being 0, we get some value input over there. Okay, so let's see how it happens to the equation. Okay, so for example, the x force equation can be written that way, and you can see on the right hand side we have delta E, which is the elevator movement. Okay. So you can see here there are 3 aerodynamic derivatives which are quite small, can be neglected when we discuss the x-force equation. So that 3 terms can be eliminated. Then we can simplify our x equation. It can be reduced to this, which we would like to see because it's much smaller than the earlier original one. And then let's see how can we do this. Okay, so before we do combine with other governing equations, let's do some simplification further. We want to eliminate m, so on both sides we divide m, and then we can, the aerodynamic derivative big XU can be written as small xu. So that's the the explanation. Okay, so doing the same thing for the other equations, and then we can combine the 4 equations together and then write them in the matrix form. So it's more concise and easier to process if we use a computer program. Okay, so you can see it's quite organized, and we can see the delta E happens on the right-hand side. And we will do this in detailed analysis for this matrix. And also, you may notice mu, small mu, it's a similar definition as small xu. So we divide the original aerodynamic derivative by the moment inertia, Iy. Okay, so let's move further, see how can we treat the this governing equation in matrix form. And so I highlighted 2 parts, and the unknowns U, W, Q, and theta targets. That's the thing we want to solve. And on the very right-hand side, that's the input term because we have the elevator deflection. Okay. So let's move on. And we call this is state space method. Why is that? Let me do some explanation. Okay. And the state space method is normally written in the following format. It's more concise, more abstract from the original matrix form. And let's do some definitions for the parameters. Okay, so we have X, we call it state vector, and the big A matrix is a state matrix. That's why we call it state space method, because X is called state vector and A is called state matrix. Okay, and then we have acceleration, because it's a derivative of X, and that's acceleration of the state vector. And on the very right-hand side, U is a control vector, which in here is the elevator angle. And then we have the input matrix, which connects with a control vector. And how do we solve this? And we use Laplace transformation for this linear function, linear equation, linear differential equation. And Laplace transformation is normally used to solve this problem. And then let's see how can we do the Laplace transformation for it. Okay. So the objective of Laplace transformation, can you remember what's the objective of Laplace transformation for this purpose? Okay, so the benefit of using Laplace transformation is we can transfer the differential equation to algebraic equation, which is beneficial, easier to solve. And then we can, based on the algebraic equation, we can get the solution of that algebraic equation. So we have that is solution, and then we can do the inverse the Laplace transformation to have the solution of original differential equation. So this is the sequence we do by making use of Laplace transformation and then inverse Laplace transformation. Okay, and so this is a typical frequently used Laplace transformation table, and you don't need to remember it. And for example, let me give an example. For example, the x dot x derivative, if the original function is x dot, that's the first derivative of x, and then the Laplace transformation is s times Lx. Lx is the Laplace transformation of the original function x. Okay, so this is one example, and then if we have xu times u, which appears in the state space function, and then we can say, because xu is a parameter, it's simply a number, so it's a knowing value, and then u itself, the transfer function is Lu. Okay, so this is a quick review of the Laplace transformation and how it's applied to solve the differential equation. Okay, so let's move further, and just remind you about the state space form of for the governing equation. And then what we do is to do the Laplace transformation, and we can do it So the left-hand side is S times the transformed X, and equals AX plus BU, and the variable is S, okay, in the transformed space. And notice here, X bar is the Laplace transformation of X, and the U bar is the Laplace transformation of U. Okay, so now let's further. So we can combine the common terms for X bar. And so moving AX bar S towards the left-hand side, and then we can have this. And you may notice there's an I. I is a diagonal unit matrix. And then we can have X bar S finally equals the inverse of Si minus A times B times U bar S. So this is transform the original equation, state space equation. And then we can have X bar. And so this is typical linear algebra problem. And the denominator is highlighted, and it is called characteristic polynomial. Because why it's called characteristic polynomial? Because it's common to all the transfer function. And the top part is the response transfer function. That's the definition. Okay, so now we can have X bar S. And then the next thing we do is to do the inverse transformation. But before do that, let's see an example. And here is an LTV A3A cos air subject to a 1 degree step input of elevator at Mach 0.3. The height is 15,000 feet. And now let's see what happens. Although we don't have those parameters, but we just give the governing equation here because we don't have all those parameters. And we use this equation, state space equation, by just putting it here. And on the right-hand side, very right-hand side, that's the elevator function. Okay, again, we write it in the state space form. And finally, we can have this X bar S, that's a transformed solution for the transform the equation. Okay, so the target is to study the short period pitching oscillation in the Fugit mode. Their characteristics like the damping ratio, natural frequency, yeah, something like those. Okay, so then we need to look at the characteristic equation. In this case, the transfer function for each variable, so we have 4 variables, in terms of delta E will appear as ratios of polynomials in S in the denominator Si minus A abstract. Okay, so this is a solution, and for the 4 parameter variables, and you can notice the denominator are common to all the 4 relations, but the difference is the numerator, which determines its specific transfer function. Okay, so since the denominator are the same, are common to all the equations, and also we may notice, you probably already noticed that the denominator contains 2 quadratics about S. Is that right? And if we see 2 quadratics when we talk about the quartic equation in the earlier chapter, and we know if it can be divided into 2 quadratic equations, and which means one is for the Fugit, the other is for the short period pitching oscillation. This is the same for here. Okay, so the denominators are the same. The denominator contains 2 quadratics for and each one for Fugit and a short period pitching oscillation respectively. Okay, so I think the following steps are quite clear and straightforward to us, and we just compare the quadratic equation with the simple harmonic oscillations. Okay, and so I'm taking U over delta E as example. The first denominator is the Fugit mode, and the second is short period pitching oscillation. And we just do the analogy with the simple harmonic equation. We can have this natural frequency, damping ratio, frequency, and a period. And for the Fugoi mode here, for this aircraft, the Fugoi mode is about 45 seconds. And for the short period pitching oscillation, and we can see the period is about 4 seconds. So the period is much smaller than the Fugoid. And also, we use this example to demonstrate the difference between these two modes. Okay, so let's move further. If we see the results in graphs, and we have 6 diagrams in here, and from top to bottom, they are U, W, Q, theta, alpha, and gamma. And we can first look at the short period pitching oscillation. The SPPO mode is almost obvious in W, Q, and angle of attack. So in these three modes, the SPPO are most obvious, and perhaps you may say the theta pitching angle also has a slight undulation at the beginning. That's true. And also SPPO completes in 7 seconds and no more than 2 cycles. So that's the observation of the front beginning part of the 6 diagrams. And now let's move to the Fugoi mode. The Fugoi mode is nearly obvious in every plot. Is that right? So it's very obvious, and its period is about 45 seconds, and it's indicated also in the last graph, bottom graph. Okay, so this is about the analysis of the aircraft longitudinal response to the elevator deflection. And so we started with the governing equation, and then although we didn't solve it, but we eventually came towards the transfer function and characteristic equation for the denominator. And then we can use a common characteristic equation to calculate the parameters for the Fugoid and the short period pitching oscillation, respectively. So that's an idea for this mini lecture. And if we compare the current result with the Lanchester model, which can be estimated, the period can be estimated a quarter of the true airspeed, which is written in knot. So the approximation is about 47 seconds, which is very close to 45 seconds. Okay, so we've seen the advantage of using this kind of modeling and solution for the differential equations through Laplace transformation. That's for this lecture. Thank you.